Hello everyone. In this presentation, I will give an overall introduction to VCK5000 accelerator card and how to use Vitis to develop acceleration applications on this card. There will be 4 sections here. First, I will briefly introduce VCK5000 card. Then I will go over the full flow to develop on VCK5000 with Vitis. Afterwards, an example design on VCK5000 will be explained. And finally, a brief summary is given. So let's begin now. First, let's take a look to the VCK5000 development card. The Xilinx VCK5000 Versal development card is built on the Xilinx 7nm Versal ACAP architecture and is designed for 5G, DC computing, artificial intelligence, signal processing, radar, and other applications. The domain-specific architecture brings strong horsepower per watt while keeping ease of use in the mind with C and C++ software and hardware programmability. Both hardware and software engineers can use VCK5000 to develop acceleration applications easily and efficiently. The VCK5000 card features 400 of AI engines running at over 1 GHz, combined with nearly 2,000 of DSP engines in programmable logic. It provides up to 145 into 8 TOPS computation capability. VCK5000 is versatile. You can use AI engines or programmable logic resources according to your design needs. In the future, the on-chip dual-core ARM Cortex-A72 can also be used for the acceleration applications in VCK5000. VCK5000 also includes 2 QSFP high-speed network interfaces. You can implement card-to-card high-speed communication with them. This is the hardware block diagram of the VCK5000 card. All the necessary devices, including firmware storage components and card status monitor modules, are included. Just plug the card into the PCI Express slot of your machine and you can start your application development. Now let's enter the major topic of this webinar: how to use Vitis to develop your own acceleration applications with VCK5000 card. You may have known that Vitis uses platform-based development flow. Vitis platform-based design methodology provides many productivity advantages, such as platform reuse, swap different acceleration applications with the same platform, application portable, port applications across different platforms with minimal efforts, fast simulation, speed up code simulation with software kernels, easy to use runtime, open source runtime that takes care of the host device communication for you, convenient debug, save the full hardware compile by code simulating the full system. VCK5000 is fully supported by the Vitis Unified Software Platform. The topology of VCK5000 hardware target platform is divided into 2 partitions, namely the base level partitions and the user level partitions. The base level partition is pre-built by Xilinx and handles basic data transfer tasks, such as onboard DDR access and PCI Express communication with host. The ARM core subsystem, PCI Express controller, DDR controller, GTY service logic, NOC, and other basement logics are located in the base level partition. The user level partition is used by the user with Vitis flow. User-defined AI engine kernels, RTL kernels, and HRS kernels are located in the user level partition. Vitis will build the partition after the user finishes the acceleration kernels design. The user designs acceleration kernels for the data and compute-intensive applications. The user should identify the performance-critical portions of the application that demand acceleration. The design of acceleration kernels can use Vitis accelerated libraries or AI Engine C language, HRS C language, or traditional RTL language. The designer will decide the suitable design methodology for different acceleration jobs. Then the developer build, analyze, and debug to verify functional correctness and validate performance goals are met. The final step is to deploy accelerated application on VCK5000 platforms. As you have known that the computation resources of VCK5000 includes AI engines and programmable logics, users can include AI engine kernels, RTL kernels, and HRS kernels in the design. These different kernels will be developed separately and built into different target files, such as LIBADF files for AIE kernels and EXO files for RTL and HRS kernel. Finally, these target files are put together and integrated into a unified hardware container file, namely XLBin file. All these tasks are finished with Vitis. The host program is written with standard C or C++ language along with XRT library APIs, and standard GNU compiler is used to compile them into a Linux executable file. The host application will load the XLBin file into the VCK5000 card and control the running of the acceleration kernels. Now let's get to the development for AI Engine kernels. AI Engine is the key difference between VCK5000 and traditional Xilinx accelerator cards. Vitis IDE provides the unified graphic user interface for the user to develop AI Engine programs. The AI Engine program uses C language along with some specific AI Engine extension. If you are familiar with C language software programming, then it might be easy for you to program for the VCK5000 AI engines. The AI Engine program is divided to two groups, AI Engine kernels and AI Engine graphs. AI Engine kernel is the core C language function block where real computation happens, and the AI Engine graph stitches the kernels and formulates the full computation data flow. From the hardware viewpoint, the AI Engine graphs is an IP block with an axis slave port, some axis stream slave ports, and some axis stream master ports. To program for AI Engine kernels, you can use three levels of programming model. The most straightforward way is to use general C syntax. This is almost the same as ordinary C program. However, since it cannot utilize the SIMD capability of AI Engine, it should only be used for fast prototyping and early algorithm exploration. The second programming model is to use AI Engine low-level intrinsic. It can fully utilize the power of the SIMD processor of AI Engine and provides high efficiency and flexibility. Another way is to use the AI Engine API, which package the low-level intrinsic as API and implement nearly all commonly used basic algorithm elements in AI Engine. So the user is advised to start with the general scalar C programming to get familiar with the environment quickly, then use AI Engine API for the real project. The C source code files for AI Engine are compiled to an object file libadf.a along with a working directory. The object file can be used for downstream hardware integration. The object file can also be used with the working directory for two types of simulation. One type is fast behavior simulation, which verifies the algorithm but aware of the low-level hardware. The other type of the simulation is a cycle-accurate simulation, which provides hardware-aware running result estimation. To compose and compile the AI Engine program, the user can use the Vitis GUI to manage the codes and complete the full flow. Or, non-project-based command line flow can be used. You can use Makefile to maintain and compile your project. It is easy to use and should be familiar for most of the software programmer. Now let's quickly review the process to create an AI engine project with Vitis. Start the Vitis. And create a new application project. Select VCK5000 as the target platform. Create a new AI application. Select engine as the target. And create an empty application. Import some source into the directory of the GUI. Set the top-level function. Set the target. And click the build icon to start the building process. Now we come to RTL kernel. RTL kernel for VCK5000 is an RTL model with the XE interfaces for control and data exchange. Depending on the functional definition, RTL kernel can access external data via XE master or XE stream ports. RTL kernel can be controlled by host via XRT, or it can also be the free-running kernel without control. After the user gets RTL files prepared, Versal IP packager is firstly used to pack them into the Versal IP. Then the kernel packager utility is used to convert the Versal IP into the Vitis kernel, namely the XO files. If you are using Versal GUI to develop your RTL models, you can use the IP packager from the GUI menu, and then execute the package XO command in Tcl console to generate the XO file. You may find that the GUI-based IP packaging is simple, but less efficient, especially for those multiple RTL models cases. So for VCK5000 development flow, we also suggest you to use the command line interface and the Tcl scripts to pack RTL files into kernels. By this way, you can reuse the IP packaging scripts for different RTL design projects. Here list some major Tcl commands may be used in the scripts, including create the project, infer exit ports, info clock and reset, set kernel arguments, associate exit master ports, and the command to execute the final IP and the kernel files packaging. Now let's talk about HLS kernels. For HLS kernel, user finishes the design with HLSC language. HLSC source codes are analyzed, compiled, and finally the Vitis kernel files are generated. The user can use open source Vitis library for their designs. Lots of fully verified HLSC models in Vitis libraries are provided in GitHub. Presently, Vitis libraries also include some AI engine models for customer design reference or implementations. When designing HLS kernels, one option is to use the standalone Vitis HLS GUI. The Vitis HLS GUI helps you to organize your HLS sources, run different level simulations, and compile or synthesize the design into Vitis kernel. Each operation in Vitis HLS GUI corresponds to a script command, so you can also use the command line flow to simplify the graphic operation. Another option to develop and maintain the HRS kernel source codes is using Vitis GUI. Vitis GUI provides a unified interface for developing AI engine kernels and HRS kernels, as well as host program. You can write and compile multiple HRS kernels in a single system project. The generated kernel files can be used in the following hardware linking step directly. If you don't want to maintain the Vitis projects, you can also use the V++ in Linux console directly to compile the HRS codes to kernel files. After you have finished the AI engine kernels, the HRS kernels, and the RTL kernels, we enter the last step for the hardware design, namely make the kernel integration. Before the integration, we need to pay attention to some key points. First, the VCK5000 target platform will handle the onboard DDR and the PCI Express access. You just need to connect your kernel to the XC bus matrix included in the user level partition of the platform. Second, HRS and RTL kernels can access the DDR memory directly via the XC master ports. Third, from the hardware perspective, the AI engine kernels only have XC stream ports, so we need the hardware data mover kernels to transfer data to and from the AI engine kernels. Last, in addition to XC master ports, HRS or RTL kernels can exchange data between each other via the XC stream ports. By the way, since presently the XIT runtime cannot control the XC engine kernels directly, so if you need to control the AI engine kernel from the host, you need to transfer some data as control information to AI engine kernels via the data mover as well. The final hardware integration flow includes two steps. Firstly, V++ link command is issued to build the hardware container. In this step, Vitis will automatically create a Vivato project with your configuration, which integrates the target platform user level partition and the user acceleration kernels. Then Vivato will finish the synthesis, placement, and routing jobs for you. The output of this step is a hardware container file, namely the XLBin file. Secondly, V++ package command is used to package the hardware container with the AI engine kernel codes. And then you will get a final container file including both the hardware image and the compiled AI engine execution objects. The final container can be loaded into the VCK5000 card by the host application. In VCK5000 card, even if you don't use the AI engine kernels, the V++ package step is needed. This V++ linking and packaging steps can be finished in the Vitis GUI as well as the command line in the Linux shell. Here shows a VCK5000-based project with Vitis GUI. All the needed source codes are maintained in the Vitis, including source code for the AI engine kernels, source code for a HRS kernel, VLV mover, and the imported RTL kernel file for the RGB mover, and another imported HRS kernel file for the JPEG decoder. When you created the hardware acceleration system project, and hardware linking project is created also. In the project setting page, you can see the 3 RTL and HRS kernels included in the banner container. You can right-click the container to set the V++ options. And finally, just click the build icon to start the hardware linking process. Sometimes, using the Vitis GUI to build the hardware is not so efficient. So, as just mentioned, a more frequently used method is the command line flow. The example design introduced later just use the command line flow, and you can refer to it for your own project. In the Vitis GUI, after you have finished the hardware linking, you can see a linking summary file generated. So just double-click on the file, the Vitis accelerator will start. It will report the linking-related information for you. You can also start the Vitis accelerator with command line in the Linux console. Vitis Analyzer is a powerful tool for VCK5000 development. With Vitis Analyzer, you could browse the hardware linking summary, view the AI engine graph and block diagram, as well as analyze the emulation and profiling result. After the hardware linking is finished, you could use Vivado to open the automatically generated hardware project. In Vitis GUI, you can start Vivado with the menu item path, Xilinx, Vivado integration, open Vivado project. You could also open the block diagram to review all the connections and address assignment, just like what you can do with the embedded Zinc device projects. You can also open the finally implemented design to review hardware placement and routing graph, timing report, utilization report, and other informations. If you are not using the Vitis GUI, you can also start the standalone Vivado session in Linux console. Now briefly introduce the host programming. After you have finished all the hardware building, you could use the XRT native API to finish the host-side programming. For the current VCK5000 platform, the host programming model is the same as other traditional accelerator cards. You just need to program for the host CPU. No A72 CPU programming is needed. Currently, the XRT native API cannot control AI engine directly, so the host program will control AI engines via the PL kernels. PL kernels act as the data mover and the command issuer for AI engine kernels. Some frequently used XRT native API functions are listed here, including some low-level function enabling the host program to write and read the kernel access slave control register directly. Now let's quickly go over a mixed kernel example design for VCK5000 cards. You can register and download the example design in member region of Xilinx official site. This is a step-by-step tutorial explaining every stage you may encounter in the VCK5000-based development. The content includes AI engine kernel and graph programming, HLS-based data mover kernels for AI engines, HLS kernel design with Vitis accelerated libraries, RTL-based data mover kernels for AI engines, mixed kernel hardware integration, host application programming based on XRT native API. This example design uses all command line interface flow, and you can refer to the makefile and the example scripts for your own design. The example design implements a simple image processing flow, including JPEG file decoding and image overlay processing. The overlay described here is a widely used image layer blending method. You can find it in Photoshop and other popular photo processing software. The overlay operation mixed two input image into one output image. In the example design, the overlay operation will mix a decoded JPEG image with a solid color layer. 3 kinds of kernels are used here. 2 HLS kernels are used for JPEG decoding and the data mover. 1 RTL kernel is used for the data mover and the pixel reorder. And the AI engine kernels are used for image processing, including the color space conversion and the image layer mixing operation. There are 2 AI engine kernels included in the graph. One is the color space conversion kernel. This kernel uses a windowed data stream as control packet, a windowed data stream as YOV data input, and another windowed data stream as RGB data output. The color space conversion equation is listed here. The other is overlay kernel. This kernel uses a windowed data stream as control packet as well, a windowed data stream as RGB data input, and another windowed data stream as mixed RGB data output. The overlay equation is listed here too, which is same as the one used in the Photoshop software. Please note that the MCU described here is the minimal coded unit in JPEG standard, which representing 8 by 8 pixel array of the source images. In the decoded image, 192 bytes of VOV or 24-bit RGB data corresponds to a JPEG MCU, and 256 bytes of 32-bit RGB data corresponds to an MCU. The processing window size of the AI engine kernels are based on MCU size. The AI engine source codes have 6 files, including the kernel file and the graph file. Here is the AI engine graph topology. The graph has one input stream S0 as the control data, one input stream S1 as input data, and one output stream S2 as output data. The color space conversion kernel and the image overlay kernel are stitched use the asynchronous window. This is HLS kernel for JPEG decoding. It uses the JPEG decoder function in the Vitis library codec parts. In the JPEG decoding process, all decoding drops are finished by the hardware kernel. The JPEG decoder function in the Vitis library have 3 ports: one input port for JPEG file data input, one output port for VOV data with MCU scan order, and another output port for image information, such as the image size, scan format, and so on. In the top HRS kernel, all the 3 ports are merged into a single AC master. Now explain the 2 data mover used in the example design. For VOV data mover, it is a simple XC master to XC stream converter, no additional operation included. For the RGB mover, besides the function of XC stream to XC master port converter, it also implements the pixel data reordering drops. From the 2 diagram, you can see that the output pixels of decoded image is in the MCU arrange order, namely ordered in the 8 by 8 data blocks. So the RTL RGB mover reorder the pixel as a line scan order to facilitate the downstream image output and display. The hardware integration step uses wave ++ command in makefile, and the customized configuration file is provided to designate the kernel connection topology. Both hardware and hardware emulation is spotted in the flow. You can review the kernel connection in the block diagram on the right. The host program example includes the basic flow with XRT native API to load Excel bin file and control the kernel execution. It will transfer the JPEG file data to the card and dump the hardware processing result from the card to verify the result. It uses standard GCC compiler and the XRT library to finish the host program compilation. Now let's get some summary for the VCK5000 card and the Vitis flow on it. VCK5000 is a versatile platform for hardware acceleration development. It provides powerful and easy-to-use connection to the card. It has great computing power, features numerous AI engine processing, and rich programmable logic resources to the user. This target platform handles all the housekeeping jobs and make the developer focused on the core designs. The software-based R&D flow makes it possible for software engineers to develop hardware acceleration applications. The supported different acceleration kernel types provides different acceleration options. And finally, the XRT native API make it easy to program the host application. So finally, here I invite you to have a try to the VCK5000 cards and the Vitis flow. You can freely download the Vitis software from the Xilinx official site and experience the easy hands-on Vitis platform-based flow. You can get your own VCK5000 card with a great price from the Xilinx website right now. Okay, that's all for the Vitis flow introduction for the VCK5000 cards. Thank you for joining us.